Okay, let's take a look at this question. So here we have lead chloride, which is a salt having low solubility in water, and then the value of the solubility product of lead chloride can be determined using electrochemical cell at 25 degrees Celsius. And then there's an information here that at cathode we have PbCl2, which change into Pb solid, and then at anode, the Pb metal change into Pb2 plus. And then here we have the data of the reduction potential related to this reaction. Now the question A, we are going to write down the balance redox reaction for this electrochemical cell. So first, we are going to extract information from this problem. So here we have the information that at cathode we have PbCl2 which change into Pb. So I'm going to write it down here. And then at anode we have Pb which change into Pb2 plus. Now we have to remember about the what happens at cathode and what happens at anode. So at cathode there should be reduction. Now reduction is when there is a decrease of the oxidation number, and then at anode there should be oxidation, so there should be an increase of the oxidation number of a certain chemical species. So in this case, let's take a look. Here, in PbCl2, we have 2 minus 1. Okay, so minus 1 is the oxidation number of Cl, and then we have 2 here, so minus 2. So in that case, the Pb here should be Pb2 plus, so it's a lead 2 chloride, and then the Pb here is 0. So we can see that from plus 2 becoming 0, there's a decrease in oxidation number. So this shows that, okay, we have a reduction here. So in that case, the Cl should stay the same, as in minus 1 stays the same as minus 1. So in that case, I'm going to add here Cl minus, but we have 2, so 2 Cl minus. So the oxidation number stays the same, minus 1, minus 1. But then, of course, we need to balance the charge. So I'm going to add 2 electron on the left over here. So now we have a balanced number of the atom and then also the charge. And for the oxidation anode, here we have Pb becoming Pb2 plus. So this is there's an increase of oxidation number. So it is an oxidation, so we just need to balance the charge over here, which is 2 electrons. So we can see that now both sides have 2 electrons over here. So we can just add the 2 reaction here. So here we have PbCl2 plus Pb, and then it becomes Pb plus Pb2 plus 2 Cl minus. Now, the question B is asking you to write the cell notation for the above electrochemical cell. Okay, so for the question B, we are going to write down the cell notation. So we have to write down the oxidation first, and then the salt bridge, and then the reduction process. So in that case, we are going to write down Pb becoming Pb2 plus. So this is Pb solid. We're going to put a separation here. So it changed into Pb2 plus, which is aqueous. If we have an information of molarity, we can also write it down. And then the next one here is writing the salt bridge. And then the next one is the reduction process. So here we have PbCl2. This is solid. And this change into Pb, which is also solid. And then here we have Cl minus, which is aqueous. Now the question C, calculate the mole of electron which flows in the above electrochemical cell, which is resulted from the reaction of 1 mole of PbCl2. So here, if we have the 1 mole of PbCl2, then we can take a look at the reaction at cathode. So here we have PbCl2 solid plus 2 electron, and it results in Pb, which is solid, and also Cl minus, which is aqueous. So the mole of electron here is like twice of the mole of PbCl2. So in that case, mole electron here is twice of mole PbCl2. So 1 mole. So we have like 2 moles here. And then the question D, calculate the change of the Gibbs free energy for the above electrochemical cell. So here the delta G standard. So we need to write down the formula. This is minus N F E standard of the cell. So here we are going to calculate first the standard cell potential. So in this case, this is the reduction or at cathode minus oxidation or anode. So in this case, we are going to use the data of at cathode. This is related to the PbCl2 and Pb. I'm going to write here. And then for the oxidation process, it relates with Pb and Pb2 plus. So I'm going to use the Pb2 plus Pb. So in that case, the E cell here, the standard cell potential is minus 0.268 volt, and then minus 126. So here we have a negative value of standard cell potential, which means that this is actually not a spontaneous reaction. So when we calculate the delta G here, this is like minus and Fe standard of the cell. So here we have like 2 mole, then the Faraday constant, and then we have the E cell in volt. So we are going to have the result in joule. So here we have a positive value of the delta G. Now let's take a look. If we want to calculate the K related to the reaction in the chemical cell, in the electrochemical cell, then what we do is so here, for example, the total reaction, we can cross this down, and here we have like PbCl2, which is solid, and then here becoming Pb2 plus and 2Cl minus. Okay, so if we calculate this as in this reaction based on the electrochemical data, then here, so here we have Q, which is not for the KSP, but this is for the reaction. So here we have Pb2 plus, and then we have Cl minus, which is square. And then if you want to calculate the KSP, which is the K here is actually the KSP, right? So if we want to calculate the K. So in that case, we are going to calculate from this formula. So we have the delta G standard minus RT ln K. And if it is at equilibrium, then we can change this into the K itself. So this one here is the KSP. So in that case, the delta G that we have already calculated, so we have like a positive here, and then we have like minus R, this is the one that we use, and then the temperature here at room temperature 25 degrees Celsius, and then here we have like ln K. So here we have ln K equals to minus 11. So here we have the value of the K as the KSP. So this is the KSP of PbCl2. Now let's take a look at the next question. So here the PbCl2 salt can be produced by mixing lead nitrate solution with sodium chloride solution. So from the lead nitrate solution, we will have Pb2 plus, so this is the source of the Pb2 plus, and from the sodium chloride solution, we have the Cl minus. And here we have the KSP of the PbCl2, but at a different temperature. So before we calculate at 25 degrees Celsius, but now we have the data of the KSP at a different temperature. Here 8.7 times 10 to the power of minus 6, and then explain with the supporting calculation to predict the production of PbCl2 precipitate when 10 milliliters of blah 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 solution of lead nitrate is mixed with blah 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 solution of sodium chloride. So in this case, we are going to calculate the concentration or the mole of the Pb nitrate. So the first here, mole of Pb nitrate here. So this is the molarity times volume, which is 10 milliliter. So here we have this, and then we are going to calculate the mole of sodium chloride, which is 2 times 10 to the power of minus 3 multiplied by 10 milliliter also. So here we have like 2 times 10 to the power of minus 2 millimole. So this one here will be the source of Pb2 plus. So we have the amount of Pb2 plus. So here we have the amount of Pb2 plus, which is 1-to-1 ratio, so it's the same. This one here, and then from this we have the mole of Cl minus, which is also 1-to-1 ratio to the sodium chloride. So here we have this value. Now, because we mix the two together, it means that now the volume total of the mixture is 10 plus 10. So we have 20 milliliter of mixture, which means that the concentration of Pb2 plus and Cl minus is slightly different. So in that case, I'm going to calculate the concentration of Pb2 plus, which is the mole, and then divided by the volume, the total volume of the mixture, and also the concentration of the Cl minus, also the millimole over milliliter. So here we have this calculation. So in this case, we have 2.5, and this one here, we have like 1. No, sorry, not millimole, but it's smaller. So here we have the molarity. Okay. Now after we have the molarity of each ions, then we are going to calculate the Q. Now the Q is calculated as the product, the multiplication of the product, and forget about the coefficient. So in that case, we have the Pb2 plus and Cl minus, but it's a square because the reaction is resulting to Cl minus. So in that case, we are going to use the data. So in this case, we have 2.5 minus 9 here. This is the Q. And then we are going to compare the value of the Q with the KSP. So we can see that the Q is like less than the KSP, which means that there are less product compared to the reactant. So if we want to reach an equilibrium, it means that it has to shift the reaction to the product, which also means that the production of the products are the productions of ion, so there is no precipitation. Now the next question, calculate the molar solubility of PbCl2 at 30 degrees Celsius in a 1.5 molar solution of KCl. So here we are going to use the original chemical equation. So we have like Pb2 plus and then 2Cl minus, and we're going to use the IC table over here. And then here in the beginning, there is already a presence of Cl minus, which is the same as the concentration of the KCl, because it's like 1-to-1 ratio, which is 1.5 molar. So in the beginning, we have here 1.5 molar. Suppose a certain amount of PbCl2, let's say S amount dissolve. So I'm going to write here minus S. So in that case, we will have like plus S and plus S over here. So at the equilibrium, we will have like S, and then this is like 1.5 plus S. And if you see the KSP, this is very small, so we can neglect the value of S over here. So this is like the same as this one. So the next one here is just calculating the KSP, which is Pb2 plus and then Cl minus square, and then we just put the value of the KSP at 30 degrees Celsius, which is this value, and then the concentration of Pb2 plus, which is S, and then the concentration of Cl minus, which is 1.5 square. So here we have the S value. So the solubility, the molar solubility is 3.86, 10 to the power of minus 6 molar. So that is the solubility when there is a 1.5 molar of Cl minus in the solution.